So, as promised, the third part of the lecture is about direct rendering, or more precisely, the direct rendering infrastructure or direct rendering module, aka DRM. Before we start, because I'm going to show this slide, I want to first show you what we see or what we don't see. Okay, so I'll go to my desktop, and you can see that we have like a couple of panels. We have also these nice floating things. We have a cursor, okay, my mouse cursor. When I go over this, I have like this very small graphic, and I also have like the icons that are small graphics themselves. And if I open something, this is like a document from like 2018 or 2019 that I stored like on the desktop and copied over and over. It's from an alumni organization that I started, and then it was later restarted very in a very marketish way. It opened like a document, okay? And if I open like here files or whatever, like you get like windows and you get like all kind of like overlay. So the thing is that this. Now I'm going back to my presentation. In my presentation, I took a screenshot. In the screenshot itself, I do not see like the cursor, for example. I do see all kind of other things, and then I have also like a little bit of annotation. We can see here an episode of The Sopranos. You can see Tony and Furio. And basically, if we did not have some hardware acceleration support, and the video player would be expecting it, we'd probably just see a black hole over here. So we have here like a window, and we have an element inside it that renders video. We have here another window. We can start moving the windows, we can maximize them, we can minimize them, and we can see several things together. One can be over the other, one could be more transparent, and each one of them would be a good candidate for something that is called plane. I'm going to talk about the DRI in a minute, but those planes, and in a very simplified way. But planes are a basic concept. Another basic concept is cursor, which is not necessarily the cursor that you're seeing right now that I'm moving. Cursor can be basically any small, very small image. And the logical idea is to have graphic cards to give them the ability to treat them differently in their drawing pipeline, in the processing pipeline. So another thing, we saw it like before a little bit as well. We can support multiple displays. So I mentioned in one of the previous parts, I mentioned like the EDID and how we identify it. This is why like the settings application knows that we have these two friends. But when I'm talking about DRI, then it's a very important thing is to know how to, what are the connectors, what are like the different screens that are connected via which like interface, and then like manage them. So going forward to a simplified diagram, pretty much similar to the one that I showed like from the frame buffers. It's simplified, it's not accurate, but it's very close to being accurate. We have here like the display that you want to display into. There are connectors. Connector can be like LVDS, can be HDMI, can be DisplayPort, can be VGA, can be DVI, can be virtual in case of a virtual machine. And one second. Yeah, so I just noticed that I had the video on, the camera on. I thought it was off, and it was pointing like to the keyboard. So you saw my keyboard. Good for you. So we have all kind of like connectors, and as I also mentioned before, like with the frame buffers, then we need to encode whatever we get. So in a format that like would actually work with these connectors, and we have like a logical module CRTC that is going to. This is what represents like after we go and take some memory and want to put it like in the chain like of drivers and processing. And this will be a logical element that actually is going to say, hey, this is what I want to display like on a screen, or portions of the screens, after I add some image and some memory. So this is great, but what happens on the other side? So again, there is a user space. In the other diagram, I put like dev fp0 here, like a frame buffer, but here we have DRI, card 0 or card 1 and so on, and that we can go and do all kind of octals on it. And so basically the idea is, and the division to memories here is not accurate. The idea is that one can go ahead and get like from a DRM driver a frame buffer memory and work on it and do all kind of like activities. And I'll show an example that means what it is. But as I showed also in the other thing, the graphic systems are complex. So the idea is to be able to have the concept of planes and cursors. Sometimes it's actually in the DRM specification, there are different things like these very small images or like a window. An image with small image or cursor would be cursor, and an image would be like image. But in some GPUs, in order to have like to represent the cursor, then you actually need to put it like on a plane. I said image, I meant plane. So the idea is that from the user space, one can have the concept of what is like a plane, or it can just work like with a frame buffer, either or, and then do all kind of like activities in order to say like to tell the driver, okay, I want to go ahead, get it like to the screen, and then it will go and go to the right, let's say RTC, figure out the right encoder for the right connector, and then like have the image. So the GPU itself, if we have this kind of concept, then it can do all kind of like operations, like blending, like overlaying, in a more efficient and logically structured way. So this is one part of the displaying in the mode setting. But what happens if we want to do, as I mentioned in the previous section, very complex calculation? So the very complex calculation are going to be done using a term called rendering. And for that, and this is also what enables like deep learning, for example, you would use not like a dev DRI card 0, you would use something like dev and DRI, render D 128 or 129 and so on, like for the first and second card, and so on. So both of these are possible, and the kernel can also plot and draw all kind of things, okay? So it can do it directly. Sometimes you can work directly with a frame buffer. Sometimes you can have planes, a compositor like Wayland, like X11, like Matter. Would usually Matter is like for GNOME, X11. There are compositors for it, but like I meant like Wayland compositor or like X11 compositor. Well, a compositor would be like Western, for example. Matter would be for both, like be for Wayland, like in GNOME. So they can go take all kind of planes and say, okay, this is how I want to like organize, and this is the concept of planes. These are your planes. Boom, render an image. Okay. So this is what we have here. And 1 second, I'm adjusting like the camera because I cannot see my own screen. Let me see if it looks okay. It's not perfect, but it's not terrible either. I'm just in the middle, so I'm not like that getting rid of the picture because it will be it will get stuck, and I'm less interested in that. Yeah, so I slightly adjusted the camera and the screen so that I will see better. And the idea is that if I have like this, I don't need frame buffer at all. However, if I want to use the FP0, dev FP0 file and mechanism, I can enable a kernel configuration called config DRM fpdev emulation, and then I'll be able to use a dev fp0, okay? And then I can also have like a frame buffer console, and then I can have like put the animation on the DRM. So if you are wondering if you use DRM and don't have dev fp0 where your boot animation is, or like where the kernel boot logo is, then this is a very good configuration to enable. Now, what happens when I enable this one? I can access FP over here, okay, dev FP0, dev whatever. Then I have like DRM FP, which is another kernel module, and DRM FP will be the consumer of this file, okay? It will have like frame buffer and then be able to do it. So to get started, if I want to have a DRM to work with GPUs, then I need to enable config DRM, and then I need to select a specific driver. So if I use QEMU, what I want, and I want to use Virta GPU, for example, then I will want to enable this config. In other YouTube videos, we actually have things for that. Now, I want to enable kernel mode settings because we want to actually go and do, put things in the right resolution, the right color depth, and so on. This is automatically identified if we want via either the command line, we'll talk about like later, or EDID, we can identify it and then say, okay, what are the supported like resolutions of this monitor and so on. But if I just need a GPU to do deep learning, for example, then I don't even know, or just rendering without displaying anything, then I don't even need to take care of like, what I display. This is another like this is another flow, okay? So just so you know, like in data centers, you have like GPUs that don't even have a lot of like features for the graphics because they don't need it. They just need to do like a lot of things. So speaking of QEMU, basically, if you don't create like a frame buffer, like in the DRM infrastructure, then it will tell you, hey, display is not yet initialized. Don't worry about it. How do you do mode settings? Usually it would be via setting. If we want to set a very specific mode, we'd do video equals the connector type, and then like the resolutions, like which one it is, and the resolution or color depth. We can do all kinds of things. Usually, we can also specify the specific driver, especially if I have like several GPUs. I'm just making it up. One Intel, one AMD, one NVIDIA. And then I can go and specify the driver that I want to use. For example, NVIDIA Novo, like the hacked reverse engineered driver that used to be. Now NVIDIA is much like more active in open source, which is surprising. So I can specify it like this, okay? Now, otherwise, I can do it with code via, for example, libdrm, as I will show a bit later. Now, the moment I do this, I can actually start working, okay, just like with a mode setting. There are other utilities from libdrm tests that it's called like mode test, and I can use that as well. Something else, we all know like the panic and the kernel panics and like the text goes like to the console, but there is a possibility to do something like the blue screen of death and actually use some graphics or some text over a DRM console. We need to disable the frame buffer console for that, so it's not exactly what you would expect. But if we do that, it still will allow you to draw like a logo via another like pipeline, not graphic, not a hardware pipeline, but like the way the software flow goes. And the things you need to unconfig config frame buffer console for that. So that's a bonus. It's something very new since kernel version 6.10, and I'm not going to get into it. Now, what I'm going to get into it is how we do our first work with libdrm. So libdrm is basically the basic. Yes, we can go to the DRM respective drivers, do I/O control, and implement everything ourselves. But it would not be very wise. So a very basic building block in user space would be libdrm that comes from the Mesa project. This is how I build it. The library itself, both like for static and non-static, both static and binary, and both static and dynamic libraries. Sorry, I'm so tired, so if I'm a little bit slow, that's the reason. What's happening then, it's a recording also, so I hope you appreciate it. We did it like yesterday, like live. So basically it uses the Meson build system, and then you do build and Ninja, and then you have like the static and the dynamic libraries. Why I'm mentioning static? Because I want to put it in the very minimal distro that we had, and then just link statically against it. So the first program I'm going to do is this one. It's going to look like this, and let's have a look actually at code. I'm going to take code, take a libdrm that I built statically, and actually I'm going to use like the include files that are installed in the system and link it statically. And I'm going to run it in my QEMU instance, because if I did it like on my host, you would not see it. But because now it's been like recorded, but it's using something else, and it uses like surfaces and panels that are inside my X, or like my Wayland based distro. So I will not do that. I will do something that you can see, that is in QEMU. So let's go ahead and see that. So I booted my little machine. Okay, this actually has config fpdev emulate, DRM fpdev emulate. This is why I can identify both of them. All right, and I'm going to go here to demos, and under demos I have the following fellows. I have Olympic pageflip, and Olympic 2, and I actually have something without the Olympic pageflip, so it's going to be under mount hosting this one. It's the same demos. All are linked statically, and apparently I forgot to mount it. So hold on 1 second. Yeah, I modified some parameter and I forgot to, I broke the lines and I forgot to put backslashes. So this was the mistake here. I'll run it again. And what I wanted to show was that if I go to mount and I put like also another resolution, then I run it to mount host DRM, I have one file called Olympic and one file called Olympic no page flip and one called the Olympic page flip. So after I go, because I have frame buffer dev, I actually have like the screen initiated. Otherwise, it will say display was not initiated yet, and my program would take care of it. I will not do it with the demo within this demo. There's a good chance that I did it in one of the talks that I recorded earlier. But let's see what's going on. I do Olympic and no page flip. We see the Olympic rings. Should wait like 3 seconds. You can see mode set and like a resolution here. And then it does some things and the screen is painted in gray. If I now went and did this again and we'll let it like I did like a little resizing, then it still works, everything is great, everything is nice. Now I'm going to run Olympic page flip. I will show the code very shortly. And look what will happen now. I draw the rings, and you see like the change of colors, and then like I draw rings again. You see remote set successfully, but you can forget about it. So what did we see here? So let's see. I'm going to quit the emulator, and I'm going to actually show the code. So I'm going to show it very quickly. So here's the thing. Maybe I'll also like upload it. We include all kind of like standard libraries, and then we include the DRM definitions here. Okay. Now these definitions actually come from one of the include files. All right. But we can see here the connector names. I mean, there is like it starts from 0. There is a list of defines 0 till I don't know what, the number that you have here. And I think 13 or 14 is virtual, which is the QEMU connector. But on like my computer, I have like an internal screen that would be this one, like EDP. And I also have a couple of like display ports, okay? So it will be like DP1, DP2, and so on. You can see also things like USB or SPI, DSI, DPI, VGA, LVDS. You can see the connectors there, okay? You can see TV. So it's very informative. And one of the nice things when you see like USB, yes, it enables you like to connect a screen like over USB, okay? So it makes sense. Here there is another thing because I'm just going to do some printouts, whether something is connected or disconnected. We have here buffer information that is going to be used in the drivers, and it pretty much explains itself, like the map with a overall size. But what we have here is something called stride or pitch, that is basically the number of pixels in each row that you have. Okay, and I'll go straight to the main function to show what it does. Optional demonstration, I did enable it. I'll show like the rest of the code later. But here are the important things. I open DRI card 0. This is like for the kernel mode setting, okay? This is not like for rendering. This is not the rendering mode, okay? And now I'm going to go to this file descriptor and get resources. It will get me a struct, and in the struct itself, I can go and start doing like the mapping of these fellows here. Like, hey, what are the connectors? What are the encoders? What are the CRTC? Hey, create a frame buffer and then boom, do like mode switching on that. Okay? So this is like a simple example that is used here. So we go over the resources. It gives us like all the connectors that I mentioned. And then it's going to tell me, hey, these are the connectors that I have. Now, you can pause and look like at the code, but so I'm going to just go very quickly. The concepts are what matter here. And here is the thing. I'm saying that if I run in QEMU, if I have like a define, I know that the connector I'm interested in is the virtual. I just want to make sure that the connection is connected, the connector is connected, okay? So if this is it, then I break. I no longer look. Otherwise, look what I'm doing here. I did it particularly for my computer. It's like a demo. If I see, I can have thousands of screens connected, okay? But I want to show this on only one of them. So what I choose here, I chose like for the demo itself, for like the lecture itself, is like to go to terminal where there is no DRM master that like F is currently active like on the DRM node. That is like the DRM node would be like the card 0, okay? Slash dev DRI card 0. And I wanted to have my computer screen available for me like for the terminal, and I wanted to have like the display available for whoever sees it like in class. So I selected the connector type that is not DRM mode connector EDP. This is why I mentioned before that this is what I had. So DRM. Yeah, so these are the names that I put here. I don't even think that I use it here, but the enum itself, it would say this name, okay? All right. So if I don't find anything, or if I say, okay, this is not what I was looking at, I'm just going to free the resource, which is fine, okay? If I don't find anything at all, it will be null, and then I'll free the resources and close the file descriptor. Fair enough. So assuming that this succeeded, I actually have a connector here, all right? So if I have a connector, this is very nice, and I'm going to go and get like a hold of the CRTC. CRTC is a logical element that represents what I want to put like on the computer. It's like one of the first elements on the chain. So it can relate directly to plane or to frame buffer, and there can be all kind of mapping. I'm not getting into this now because right now I have something very simple. I want to have one frame buffer. I'm doing the simplest thing and put it on one display, and I'm going to use one CRTC, okay? So I'm going to check now what are the modes that are available for my screen. If you use like the mode test util for libdrm, you'll see like a list of modes that it supports. I'm going to set this mode, and look what I'm doing. I'm going to create a frame buffer, all right? And the frame buffer will be associated with the buffer that I declared on like earlier, okay? Which is this struct if I find it somewhere. Let's see. This is not main. I'm looking for main. And you have to forgive me. Yeah, so this is it. Like this is like the struct, like with the stripe, with the mmap, with this. So I just wanted to show that. Okay, sorry for jumping. I just wanted to triple check that there is no other definitions to see that it was defined statically. I defined it statically. We're all good. Like okay, I defined it like that I defined it locally. We're all good. So we were here, mod set create frame buffer. Forget about the cleanup. If things don't go, we clean everything, we close the file descriptor, and that's it. First, what we do is clear the frame buffer to white. If I put here another color, you would have like another background, all right? And you'll see it like later in one of the examples. Then we draw something. Actually, this function doesn't matter at all. I'll go and look at it later, but assume that we draw this Olympic rings because that's what we did. And then like what we do a DRM mode set CRTC, and with this we actually do page flipping. It's not double buffer and triple buffer and something like that, but it's a way to avoid, if we do several drawing, it's very important, okay? And I'll talk about it a little bit later. So in our example, I do optional demonstration that actually does both of the things that are listed here, draw Olympic and draw mode set RTC, but I will get to it later. And when I'm done, I get any key, it doesn't matter. I unmap the memory that I got earlier, and I'm freeing the connectors here, okay? So these are the lists of steps that I had, all right? And one of the things that, what I unmap is what I do get when I do like the mod set create a frame buffer. All good. So far, so good. And I draw something that doesn't matter, okay? That's what I mentioned. What do I do in the mod set create FB, and what do I do unmap to later? So what we do here, we actually, this is where graphic processors usually would have the capabilities to give you a buffer to work with very effectively. If they don't, the DRM framework can provide you what is known as a dumb buffer. And a dumb buffer is just like a matrix in memory, and that's it. So this is what we're going to use here, okay? So we call it create, all right? We have like a map, and we have a handle from system, and we are going to here go and set the resolution, the parameters that we got. So look what we have here. Where is the call? The call itself is, we get it like from here, fd mode, fb id, and buff. And the mode parameter, this is where we have it here, right? The mode horizontal and display, because we did like mode setting. We got the first available mode, okay? Now, we select the depth, which is 32, which means like 1 byte for example, for R, 1 for G, 1 for P, 1 for alpha. And now we create the buffer. This is the IO control that we do. And we give it this create parameter, okay? Great. Now, after we do that, if everything works perfect, if not, okay, the handle is going to be the return, the value that we get from this IO control inside, all right? And we actually now go to the buffer object. We have like a frame buffer, dummy buffer object, and we go to the buffer, and we are going to assign this frame buffer to the handle that we got from this dummy buffer. So this is how we like match a frame buffer, a memory that we will work on, with whatever is available, like in the particular, in what the kernel assigns to us in the dummy buffer. But if we use like a real graphic cards, then they would assign us a dumb buffer that is probably DMA-able and so on. Okay, you can do all kinds of things like immediately. This is very important. For example, if we work like with video, if we work with the cameras, etc. So these are pretty much stated themselves. Like we put like the same resolution that we had. We put the same stride pitch that we had, the 32 bits. And what we do now is go and attach both of them. Okay, So we do DRM mode add FB, and we do mode map to this map that comes like from, this is this guy, okay? This is the second one that we add here, all right? So we do the mapping, we map the dump buffer, and the last thing we do, all of these have to do, I mean, they're kept internally in the kernel, like in this driver. Once we've done that, we actually want to have a memory that will work with in the application. So we do an mmap. We tell it, hey, please give us a shared memory over there. So you can see that it's map shared. We can see that it goes via the map offset, whatever it says. And you can see that the size is a create size. All right. And it's the offset like from the frame, the file descriptor that we opened. So it's the map offset that was given to us when we created like the frame buffer. So this is our control again on the device that we have, like the file descriptor of dev DRI card 0 that we opened. So this is nice, and if all works, we can just go ahead and write pixels to this memory. So this is pretty neat. Let's go forward here. So that's mode set create FP. And yeah, we covered everything except for the growing. We covered the most important thing. So once we have a frame buffer and we have a mapping to it, like to a memory that was assigned for it, we are good to go. So what does this function do? Like this grow Olympic. Before this, we have, okay, memset to the buffer that we allocated in the background. I already mentioned that it paints it like with white, but I didn't mention how we get the buffer. We just cover it with this function. Okay. What do we have next? So what we have is a couple of functions that I will not even bother to mention all of them. We have a list of color, like an array of color, and we're going to have like the positions and the radius to draw like each circle. And what we're going to go is go to each one of them. Okay. There is also an opportunity to do like colors if I want to do like if I want to have backgrounds here, and if yes, great, and if not, no. If no, then the background is white and I don't care. But the idea is I'm going to move the position and then draw a circle, like this color has already been like selected. And what I can do is just go ahead, move like the positions, like in the loop, look at the radius, okay? From minus radius to radius, I'm just going to draw pixel, 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 okay? And move it. And look what's going on. I'm going to, where I'm going to draw the pixel, like each one of these, like a draw Y, and like the width, and draw X is that position. So I'm just going to put it here over like the buff map. This is like direct assignment. I put her the respective color, and this is how I paint. So this is what gives me like these Olympic rings. And I wanted to actually go and talk about one more thing. So optional demonstration that was called here does the following. After we paint the rings and call DRM mode set RTC, actually now one of them is combined with and one without, like this naive page flip. We do a sleep, okay? We sleep 3 seconds, and then we do some things. Look at this. Once again, I write to the map. Remember I told you about the color, that it was all white. Here we do a loop, and we start from 0 to 19. So every time we are going to set it 0, and then 10, and at the end 190, like the color. And this is going to be to give us a grayscale. All right. So there are two options here. If I do these activities, DRM mode set CRTC, you will see one thing. And if I don't, you will see another thing. And I sleep like at 100 milliseconds or 10 milliseconds in between it. Okay, you can see the number of zeros here. I think 100 milliseconds. So after this, I'm drawing the Olympic rings again. This is what we did, all right? and it will be over like the last color that I had, if this indeed worked. And after that, once again, I call DRM mode set CRTC. So DRM mode set RTC basically forces me like to sync. This is the page flip, okay? And if I used a device that is not an emulator, now let me run this again. If I use the device that is not an emulator, let's go to moment most. Because I don't remember which one is which Olympic. DRM. So with a no page flip, this is where the naive page flip is not defined. I could see anything that has to do like tearing or something like that. Look what happened here. I just saw like the gray, and then So in other devices, there is a very good chance, like on my computer, if you saw it, you would see that there is like one line that changes the color and the rest doesn't. So the thing is that I cannot go ahead, write to write to the memory whenever I want, when it is possible that some of the memory is being used by the GPU itself at the same point. I need to tell it, hey, this is when you draw, or this is where you change buffers. There is a buffer you work with. I populate another buffer, and then when I'm done, I'm telling you, hey, this is like your time to do that. So if you are the relevant terms can be something like page flipping, and the relevant like technical terms can be and vsyncs that you might have, vblank, and so on. Like when you do like the syncing itself, horizontal syncing, vertical syncing, and so on. This concept actually come from the good old days when there were like actually cathodic ray tubes print. So this is what we see when there is no page flip. And with page flip, you will actually see the right behavior. Wait 3 seconds after we draw, and now we'll start seeing you see the background changing, like everything they do is actually happening. Okay, so nothing has been missed, no screen tearing, and so on. And as I mentioned several times, the reason why you could not see some things sometimes is simply because of the implementation of Vert IO GPU and my computer. Great. So we covered that. We saw our very first example. I'm sorry, when I look at it like in the computer, like compared to yesterday, everything's so huge to us. So we managed to do DRM without anything else, which is amazing, okay? To do like direct rendering, which is pretty amazing, okay? Now, usually what we did now is we got buffers somehow automatically. Usually it's not the way it is. I already mentioned that there are ways to get buffers, and there are ways to get buffers that actually cooperate with the GPU to make things efficient. So usually you will not only use libdrm, it's not enough, okay? You will need additional constructs, and usually you will not just do something that simple. You'll do things much more complicated. You will do all kind of like swifting the images, blending pixels that are one next to the other, want to do all kind of like very complex computations, and want to do, you know, overlaying and shadowing and calculate all kind of models and do ray tracing and that and that and that and that. So a lot of these things can be done in parallel. A lot of these things can actually be even like an entire program that is meant for that, which is basically known as like shader. Like I mentioned here, like in the past in Android it was render script, now there is AGSL. You can write little programs that are like compiled differently, that the GPU knows to use its tons of cores to actually execute it. So with this framework of DRI, DRM, you can do a lot of things. And because you can do a lot of things, and you need to understand how your hardware works, but some things are very common and very powerful, there is no way you're going to just go and draw a circle. You will use constructs that other people use, that other people do, and there will be other libraries like OpenGL, OpenGL, yes, which is like more for embedded, and Vulkan, which is much more complex, much more low level, for embedded, for non-embedded, relatively new. And this is like the next talk after this one, but be aware that the other talk is in Hebrew, but perhaps captions will be good enough. And the speaker is amazing. It's from ARM. They actually work on this, on enabling Vulkan on Mali GPUs. Okay. So we said we need libraries. So the de facto standard for libraries on PCs would be Mesa on Linux, and Mesa also provides libdrm that we met, and it also provides implementation of Chronos, OpenGL, OpenGL, Vulkan. It enables Gallium that has like abstraction layers and so on. You can see some of the available features like in Mesa Matrix. Okay, all kind of platforms can have their own implementation. That's good. That's fair enough. Having said that, we already saw something that worked like really well. But since we already mentioned some libraries, it's a good time to now go ahead and use a system that is actually full and show a lot of things. I mean, not just a minimal system or route to another system. Let's go ahead and use a kernel that supports quite a lot of features. In the other videos, I told you also how to enable things in a minimal configuration and how to trace it, how to understand how things are. But now we're going to work on something that is like fully fledged. Okay, so I'll show a couple of examples. Okay, I mean, some of them I can actually show right now. If on my host, if I have like OpenGL, I can do something like this, a GLX gears, a GLX info, or do even all kind of, I hope it will not ruin like the recording, but all kind of like benchmarking, like GLMerk2. We'll see here all kind of things that are running, and it's like nice, and it will give later a result. Okay, the side it will say what it does, how much it grows, right? And for Vulkan, you can also see like the Vulkan cube that we'll see later. This requires you to have like a display server like X or Wayland for VK-Cube X11. However, there is something that is known as KMS Cube. And KMS Cube does not require any display server. So let's go ahead and look at it when I will run. This was a nice example. Thank you, Olympic. I will now go ahead. I can run it also on the same one, but I closed it actually. But I will run it on another emulator instance that I put here. Okay. This is from the previous lecture, I think. So let's go ahead and do KMS Cube, and voila, you see something very graphical and very nice that even has like a relatively nice frame per second, even though it uses like for GPU. So you see what we have here? We ran OpenGL very nicely, and it even bothered to restore like our previous graphics before. Okay, so this is nice. This is pretty cool. And we have a frame buffer 0, so let me just go ahead and cut dev 0 to dev fp 0, and then I have like that. Okay, so this is cool. Now, what is KMS Cube linked against? Quite a lot of things. You see now why I put like a fully fledged system? So it's linked against a lot of things, and while at it, we can see VK-Cube that I showed in the other thing. I'll do LDD, which VK-Cube, and it uses a bit less things, but it needs X11. Okay, so this is not so nice. All right, and if I use VK-Cube Vulkan, I think this is how it's called. Wayland, sorry. Of course, Vulkan is like the. Then I'll see. Whoops. Then I see that it uses like a Wayland client, And then the Wayland client will say, hey, compose this and that, and then, yeah. So this is like what we have, and Vulkan uses much low level information. There's another lecture about it. So we also show a demo of QEMU, okay, of KMS Cube, and this one is actually quite powerful, uses a lot of things. It does not use only libdrm, okay, it uses a lot of things. If we want to go ahead and build KMS Cube from source, we can do it, but building it statically and having all these libraries, it's not so easy, because you need to build everything else statically, because the dev packages are unfortunately not given to you like this. This is why I use now Debian. You can use Yocto, you can use whatever. How KMS Cube looks like, or how does like Meson look like? So if I wanted to go ahead in the Meson system, link foo.c with libdrm, like if I want to do it for the Olympic example that I wrote, then this is how we do it. We say lib dependency, libdrm, use the static version true, and so on and so forth. And I can also go ahead and use like a link args static here. Now, in the KMS Cube, if you open like the Meson build file, you will see that it has like the dependencies. So if it finds a libm, great. It needs libc because everything uses libc threads, nothing to do with the graphics. libdrm, I myself, after I built it and put it like in the libraries and library finding path, I said, hey, please make it static. GPM enables you to more easily get buffers, okay? So it requires this version, and this requires KMS Cube, EGL, and GLES v2. So these are things that are, this is graphic buffer management, by the way, GPM. So it needs all kind of things. And when I install it, like in Ubuntu or Debian, look at its dependencies. So it has all kind of dependencies here, like this is like all the things that like it has. Like you can compile it to use like libgstreamer and show all kind of things. You need to have like the Mesa. I actually have no idea why it requires the X client protocol or like the Wayland, but maybe there is like another in this package. Maybe there's KMS Cube that runs on Wayland or an X. Could be. You know, just for fun. Yeah, so it has a lot of like it has a lot of options, right? So it's pretty nice. A video, it can show you like the video list. This is why the GStreamer, okay? And we can use surface mode, and we can have all kind of like things here, which is pretty nice. It is nice, okay? But this is not the topic. I'm getting drifted because now there is no crowd, but I want people who watch it to not waste their time. So the dependencies are great, but if I try to run it like this, it will not be able to do anything with the GPU. Why? Because the GPUs require a DRM blob usually, and each one needs like its particular driver. So fortunately for like VertIO GPU and for many other drivers, also for NVIDIA, for like Novo, but also for like i9-15, for Intel, for the Radeon, where there was like ATI, for some AMD stuff. Actually, Mesa implements this as well. Remember that I talked about Mesa in its project. So it also has like tons of like DRM drivers. So I install it, and then you can see like this nice cube. So this is great, but for this KMS cube, Mesa is heavy and everything is heavy. So when you want to take into consideration these things, you need to understand what you want, like size, performance, capabilities. There is no way around it. So just looking a little bit about like libraries. We have here several things on the screen. We have the graphics like here, down there, CPUs, also GPU somewhere. And the thing is like this. if we have like a 3D game engine that needs to do rendering, then it can go and use directly the OpenGL or the Vulkan. I added Vulkan here myself. This was mostly GPL libraries, and it can use, for example, here you can see like proprietary drivers that can use that know like how to work like with the hardware with DRM frameworks. But there are also things that are like part of Mesa that actually come here like for you. So Mesa also helps us install libdrm, Intel, Radeon, and so on and so forth, and with very specific things. So we have like the DRI like for this and for that, and like it has several things here. Okay, so who uses this and who uses that? Both the application can use, all right? And if you have like a compositor like Wayland or Xserver, they can also use like directly libdrm, access like the hardware, and basically Wayland uses directly it uses like the Mesa API and then uses like the more low-level stuff. Modern X also does the same, and when you have like a Windows managers, then they use like a client to work like against like X or Wayland and so on. Okay, so when you see libWayland client or libxcb, these are like the protocols that the application use to talk like to the display server. So tons of libraries, all right? So it's very important to understand what you need, okay? Very, very, very important. Otherwise, just wanted to see, yeah. Otherwise, everything will get very bloated, very, very, very bloated, very easy to get like to gigs over gigs over gigs over gigs. Now, if you want to educate yourself about OpenGL and Vulkan, actually the builds for OpenGL are relatively light. The demos are here under Mesa, and you just build them with Meson and Ninja, and then you can run them. Almost all need to be over X or over X-Wayland. Vulkan is something else. When you just download it, it's going to be like 2 gigs, just like for the source code, and building it will take a while, but it works, and you have very nice examples as well, and very powerful examples. Now, if you want to just show the VK cube of Vulkan, you need to have a display environment, as I mentioned, and in this particular environment, that I also look at this. It's like 4 gigs. I put here Qt Creator like for the demos, and here I already put both like a GNOME and KDE and Weston, which is what I'm going to use. Okay. Right now I'm in multi-user mode, not in graphical. So I put here Weston, and I will put VK Cube Wayland. And you can see here as well, I press space and it paused it as expected. Okay, now I put it again, and this is fine and this is nice. All right, so this is what I have here, and it's pretty nice. Okay, the running with cursor here is pretty annoying, but no worries. Okay, so basically, if you want to use Vulkan, it's also very simple. For KMS, we do, KMS Cube or like Mesa or Mesa Utils, one of them. Actually, there is like KMS Cube package here. And for Vulkan, we need to have Vulkan tools, and we also need to have specific Vulkan drivers. Otherwise, if we just install like Mesa, then we can go ahead and see, hey, it does not support it, even if you have like the best GPU in the universe. And a very indicating message that say, hey, you don't even have the minimum to run Vulkan would be something like, hey, cannot find this or that feature after enumerating instance extensions, and that would be VKKHR surface, which is like the most trivial thing. So if we do that, we can run VK Cube over Wayland or over X, and actually showed you both. One more thing, if you have KMS, if you have DRM, KMS is for kernel mode setting, it means it's part of the architecture, okay? KMS DRM. If you have that, then you can, and you do not have like a frame buffer emulation enabled, DRM FPTF emulation, then you need to use another mechanism to show a splash screen. And pretty much everybody uses something called Plymouth. And it can also fall back to using frame buffer if you do not have DRM. So just be aware that it exists. So this is pretty much what I wanted to cover, okay? Because I already showed you Weston in another video. I already showed how big it is. I already showed all of the cute example in another video when I do like the Bluetooth. And I talked about sizes, and since then I also added something that actually uses an entire display manager. So this was and hardware accelerated. So this was let's see. I'll do system control, isolate, graphical. I should have taken off Western, I suppose. And I'm pretty sure that I had this. Maybe I was already there. You know what? And I don't think I was. Multi-user. Maybe it just takes like time to load, but I already showed it, so we're all good. Yeah, we see GDM3. And it is possible to play with thing, but I believe that it will load, you know. It's not all bad. And if I reset it, it will definitely load. So now it lets me do that. Of course, not this. I want to reboot. So here here I have frame buffer enabled. This is why I see this, and I see this much penguin because I did like with multi-core, and I believe reached the target graphical target. There is a chance that like on the demonstration yesterday I destroyed it. So here we have like user, and here we have the session that we can like select. Let's select like Ubuntu here, and I will let it log in. And basically, with this, I can say that that we're done. So it's pretty nice. Let's go to our summary. We talked overall about 2D graphics, the limit kernel user space, mentioned some trivial ways to display the screen via FPTF. This was like in part 1. Discussed library dependencies and trade-offs. Also did this. Showed some demos of some 2D libraries in part 1 and part 2, and also in the accompanying video. Talked about Qt and showed how to do like Bluetooth with several devices. I'm looking now for the board that I had here somewhere, but I put it in the back when I went to speak at the meetup. And now we also saw DRI, and we saw a 3D. Actually, this is missing here, but we saw also like how we also did like a DRI, and we did DRM, and everything was pretty much, we did a pretty good job, right? So let me just edit it so that it will be accurate. This is very, very, very true, right? Showed the concepts of DRI and related and important, let's say, libraries. I want the summary to be short. So this is what we've done. And having said that, we're done with this part of the meetup. So thank you. And I hope this was useful for you. And you are more than welcome to contact me if you have questions or requests. Just one thing, if it's a request about the volume of part 2, please try to put captions on, and please try to just use something with a high volume. If 1,000 people ask for it, I will record it, okay? But otherwise, yeah, I mean, I prefer to do some other things. But yeah, if you find things useful, please let me know, and take care. And have a good day, afternoon, or night. Bye bye.